Alan Neese from Hydrogenics. We're a company that does electrolysis and fuel cells, operating since 1948, so a long history in the business, and here to talk more about the applications that we can also provide the mining industry.
Thanks, Matt Marinovich, Baker Hughes, GE. Primary purpose, I suppose, for sitting on this panel is our association with the development of 100% hydrogen-fueled gas turbine technology for power generation.
Warner Priest, Business Development Manager for Emerging Technologies with Siemens. Siemens, large German company, approximately 370,000 employees worldwide. And we're really an electrical OEM, so we do everything electrical. And that's exactly what these electrolyzers are all about.
My name's Andrew Dixon. I'm part of a consortium developing a project called the Asian Renewable Energy Hub. It's a large wind and solar project in the East Pilbara, conceived as an export-oriented renewable at oil and gas scale. It's been shifting in focus and ambition from exports of electricity via subsea cable to Java and Singapore. That's still a possibility, but really our focus is shifting to the possibility of large-scale production of green hydrogen and derivatives. So by that I mean hydrogen is a master molecule that can be used to make many things. Ammonia is one possibility, methanol, other chemicals. We have lots of cheap, clean energy, and we plan to produce and export primarily those products, but also they're highly applicable in the Pilbara as well.
Great. So to kick off our first question for today's panel, what are the main considerations for mines when assessing on-site hydrogen production? Someone want to take that one?
Yeah, so from my side, it's a couple of things. It's the cost of your energy. So if you have both wind and solar, complementary wind and solar at a particular site, and it's a good resource, you have a low input cost to your electrolyzers. And this plays a very, very important role. The other is obviously the availability of a water resource on site. So you need those three components when you're looking at renewable hydrogen production on site. So those are the three key factors from my point of view.
I'd like to reiterate a point that Warner made in his presentation, that really the secret is in how to hybridize different technologies together. So solar on its own has a relatively low capacity factor, typically around 30%. And that means that expensive capital equipment, electrolyzers and so on, they're expensive pieces of kit that you need to use as much as you can, high utilization. So you need to hybridize with particularly wind and solar to get capacity factors up, to get the cost of hydrogen down. So our project is 2/3 wind, 1/3 solar. Obviously solar is ubiquitous across the Pilbara, but wind isn't. So we've selected a site that has really good wind resource, that's very complementary with solar, and by combining the two together and overbuilding cheap generation, we can deliver energy to the load, the expensive load, with a capacity factor of around 70%. So from my perspective, at a small scale, with solar only, the cost of hydrogen is going to be quite expensive. An alternative is to centralise and scale up enormously the production of hydrogen and derivatives to then distribute across the region.
Andrews, can I ask a question there? What is it that you're expecting to do as far as your water is concerned?
So yes, we do need a lot of water. So we are planning a desal plant, about the same size as the desal plant of a small city. But again, given the scale of our project, it's relatively trivial, the energy and cost impost of that.
Just to add, I think one of the things also about paired electrolysis, which both Siemens and us support, the variability of moving the power up and down is fine. It doesn't hurt our systems. The systems are really, really reliable. Electrolysis equipment, we've had systems deployed since 1948. We've retrofitted stuff in the 50s, 60s, and 70s. They're still running at power plants and steel manufacturing. So So this equipment is extremely reliable, so we're not too worried about that. Having people understanding the equipment is important on site. I think that's, to your question, you always have to make sure that there are people who understand this equipment, but we talked earlier in the day a lot about training and such, and a lot of that skill set is here anyways. Retraining towards hydrogen, I think, will not be the hardest thing to do, and as mentioned, you're going to need a lot less people to maintain this equipment. I mean, diesel generators are really old technology, need a lot of moving parts. Our systems are very different that way.
Great, so we've touched a little bit on the economics in that question actually, but to expand on that, how much energy spillage from renewables is needed to make hydrogen production economic?
So I touched on this a little bit in my presentation. It really depends on the particular site, and this is where, why it's important that if you're going to embark on this journey to work out what makes sense for your particular site, that you do the techno-economic assessment modelling beforehand. Every site is going to be different, and it is where you start. You've got to verify that you've got the right resources to fund that capital outlay around the hydrogen. And it's how much energy that you're going to spill, what's the value of that energy, and the life of mine is very important. If it's only 3 years, it's very unlikely that it's going to work. If it's 10 to 15 years, it's more likely to stack up.
And I think also the size of your plant, everything is about scale. People always ask me, where's our price going to be in 5 years? Well, if I'm producing 1 or 2 megawatts of electrolyzers and 1 or 2 megawatts of fuel cells, it's still going to be bloody expensive. But if I'm producing hundreds of this equipment, or I've got large projects here and other locations in the world, in Europe, etc., then our price will go down dramatically. So if you're thinking about projects in the audience, you got to think big. I mean, maybe that first one will be a small one, but to get the economics there, where we're comparable to diesel and other technologies, everybody's got to start thinking big, or it's not going to happen. And you need first movers. You need, the mining companies that are here. Talk to Komatsu. Tell them, I want a hydrogen vehicle. Right? Tell them, give me your hydrogen vehicle. They'll talk to us, Ballard, and others, and say, we'll build you one. But if we're just sitting around waiting for it to happen, it's never going to happen. Right? So we got to start thinking of these big projects and start moving, or we're not going to get to the Paris goals and our 2050 goals. So we all have to think big and think large scale, because then your economics will be very attractive.
I mean, right now as OEMs, we're building this technology in large workshops. We need to move to large automated factories, and we need those automated factories to be housed here in Australia, because let's face it, there's no other country like Australia that could take advantage of this impending new renewable export industry around hydrogen. So once that happens, those prices, the capital costs associated with electrolyzers and fuel cells will come down, like we've seen with batteries and solar.
Yeah, I mean, for context, the growth in installed capacity for renewables and the corresponding drop in price it's way more than most people realise. So the levelized cost of electricity from solar PV has come down about 90% in the last decade. Wind is about 70% in the last decade. Solar installed capacity is growing at about 28% compound growth. It doubles every 3.8 years. So think about that as a curve projected into the future. Wind doubles every 5.5 years. The first 1 trillion watts of renewables were installed over 40 years, finishing last year. The next 1 trillion watts will be in the next 5 years. So it's really dramatic. And so from the generation side, it's obviously well baked, it's well advanced. From the electrolyzer side, we're only really just beginning. We should see drops of probably 70% in the next decade. So yeah, the technology is moving very quickly, but also the market maturities, or ambition initially, and maturity are also growing quickly. So yeah, our project was conceived with really huge ambition, really nothing short of creating a new export industry for Australia, making the most of our abundant wind resources, solar resources, land and seawater.
It's also important to note that 75% of the cost to produce that hydrogen is actually the input energy cost. The electrolyzer only makes up about 5, 6, 7% of the total cost to make that hydrogen. So it's very important. The input energy cost is a big driver.
So we've got other energy storage options available as well, other technologies. How can hydrogen work with other storage technologies to meet the mining energy demand?
Okay, so look, from my point of view, hydrogen and batteries will coexist. We keep on hearing this term fuel cell electric vehicle. It's actually a hybrid. It's both a battery and a fuel cell. So it's a battery to get your performance on your vehicle, and it's your hydrogen and your fuel cell to get your range. And the same thing applies for stationary power. A remote area power system will have a battery. The battery will be there to provide your grid forming and respond in that millisecond time frame, and it's your fuel cell that will provide the length of time to output your energy stored. So the two will work hand in hand. But there are other storage mediums that we will continue to rely on for the foreseeable future, and that is our diesel fuel and our gas fuel. They are the fossil fuels that we rely on for storage today, and probably will rely on for the next decade or two. What we can do, however, quite easily is reduce our reliance on those fuels by approximately 70%, where we've got complementary solar and wind. And we'll see more and more of that happening over the next 10 to 15 years.
I mean, one example, we actually did a mine in northern Canada, had a megawatt electrolyzer, 200 kilowatt fuel cell, and had a flywheel as well as another storage technique. I think working with multiple technologies will be common. You're going to have various consultancies, companies like Siemens, who have that capability to match all the technologies together. And I think over the next many years, it's hard to say who's going to win or whether there won't be a winner and there's just going to be multiple technologies in storage, which I think will be the case for the foreseeable future. The goal is eventually to phase out diesel, and I think that will come, but it'll take time. So.
The secret is absolutely hybridizing, but even the most entrenched old school fossil fuel generation source, coal, can also be hybridized with clean fuels. So about a year or two ago, Japanese researchers established or demonstrated that you can actually co-fire up to 20% green ammonia in a conventional coal-fired power station with very minimal modification. So in that way, they can actually, by co-firing at 20%, they can drop the emissions by 20% in a coal-fired power station. Doing that across a whole fleet in a country can reduce national emissions by a very considerable amount, just by hybridizing, introducing a new clean fuel and co-firing. So that can be done at many different scales with different technologies. The secret is hybridizing in the right way.
And Siemens have also done a lot of research and development around our burners on our gas turbines. So we've done research on running ammonia as a fuel, so 50% ammonia, 50% hydrogen on a gas turbine successfully. And also we have 3 of our air derivative gas turbines can run on 100% hydrogen. So there's a big change in the OEMs actually developing, like GE, the capability to run their gas turbines on 100% hydrogen and or other green fuels like ammonia.
Just to add to Warner's point, I mean, he's absolutely right. We've been burning hydrogen in our gas turbines for a long time. It's not essentially something new or it doesn't require too much advancement in the technology. It's been happening for some considerable time. The challenge really is around, the stepwise challenge will be to create a turbine that can run 100% hydrogen all of the time, and that will start up in hydrogen as well. So we've seen for a number of years across a number of countries and applications, baseload power generation or otherwise, not only the ability to run on some blend of hydrogen, but to Warner's point again, to run on a variety of fuels. That could be biogas, that could be coke ovens gas in some stages. There's no real limitation in terms of the quality of the gas. In theory, of course, the work needs to continue, but we welcome the chance to adjust the technology to fit the application in that sense.
So what would be the main barriers of integrating this technology into the mining powering systems?
I can start if you like. Yeah, I mean, at the moment, we are in the process of developing, a gas turbine, like I said, 100% hydrogen. This particular gas turbine will be based on a specific size, 16 megawatts in our case. Now, as long as a miner comes to us with a requirement for roughly 16 megawatts or some multiplication thereof, we feel we're in a good position to be able to sort of have that discussion around supporting them. So, as usual, I know there was a discussion this morning around starting with a prototype, starting with a demonstration plant or whatever the case may be. Well, that's no different for us, where we need to firstly prove up a concept or a machine at a particular size, prove that it works, with a partner or partners, hopefully. And then once that happens, you then generate the stimulus to develop machines across a broader range of power demand. So that really therein lies the challenge. I mean, the cost is always going to be a challenge as well. I can't commit to a 70% reduction in cost over a short period of time on our equipment, but most definitely as the technology evolves and matures, we're going to see a dramatic decrease in cost as well.
Ours would be a real-world example. We can do anything from 5 kilowatts up to multi-megawatts. We're modular in terms of the electrolyzer and the fuel cell. I point to a real-world example, which was our Raglan Mine project. It died, be very open, I'm honest to everybody, because a heater broke. And the integrator didn't check to make sure that they had monitoring on the heater. So it froze our electrolyzer. Fuel cells were fine, or at least our fuel cells can freeze, no problem. But it was minus 50 and the electrolyzer froze. And so the message here is that you got to make sure as integrating these projects that everything is monitored, especially in the remote location. There they didn't have people, the heater froze within a week, nobody came. And of course, the equipment had, a meltdown, if you want to call it. So for us, it's really making sure that you have a very integrated approach and all the equipment is monitored, and you have service and support if needed.
Yeah, from my perspective, doing a lot of these techno-economic assessments is CapEx. There's CapEx shock. We saw in my presentation 28 million for a diesel plant versus 158 million for a hybridized hydrogen plant to fulfill the same requirement. The other is life of mine. We need mines that are going to be greater than 15 years, preferably 25 years, for these things to go ahead right now. And then the other is confidence in the technology. There's not enough risk-taking, especially here in Australia. We need to take more risk. These components are far simpler than diesel engines. We need to train the people and bite the bullet and go for it.
Yeah, there are lots of chicken and egg scenarios here where, for example, with fuel cell electric vehicles, obviously people won't buy a fuel cell electric vehicle until there are hydrogen refueling stations. Commercial operators won't build the hydrogen refueling stations until there are enough vehicles. And I've also heard it described as rock, paper, scissors, because the suppliers of all the components for the cars and particularly the refueling stations can't realise economies of scale before both of those things grow. So we're kind of caught, with the rock, paper, scissors on, in the mining sector as well. And it will take visionaries to actually just say, look, we're going to do this, and then start growing, set targets and make it happen. So yeah, it will happen, but we do need leadership, people who are prepared to sort of work towards the future, because the future is definitely heading this way. The question is how we get there. It's non-trivial.
Just to add to mobility too, something we didn't really talk about a lot was the technology is there. We're making trains, we're making trucks today, we're making buses available today that can be easily brought to Australia on a moment's notice that could be imported. Mining is about fleets. So at the end of the day, you need fleets of trains, you need fleets of trucks. Those things are available today. And the example I always use, China has 1/10 the fueling stations as Japan, for the same amount of fuel cell vehicles, roughly. So when you're talking about costs and mitigating costs, I love my friends from Hyundai and Toyota. I don't know if they're here today, great guys, but honestly, I think fleets is more logical at the beginning. Buses, trucks, trains, because then you mitigate that infrastructure cost of a fairly expensive fueling station. I mean, compression and storage is not that cheap yet, and I think that's where we need to look at it, is mitigating those costs for greater adoption early on.
I just want to take it back to you, Warner, for a second, on your comment of 15 years mine of life. As technology develops, do you see that coming down? Because we do have quite a lot of miners who may only mine in certain pockets of areas for a year to 5 years.
I'm not sure, because what we're moving into is a phase where essentially we've got free energy and it becomes a finance game. And where it's a finance game, it's about paying off that equity and debt over a period of time. So it really depends, but you know, we're seeing the Goldfields mine, they're probably going to introduce wind at some point, and you know, what's the value of that curtailed energy? We know that they have short periods of mine life, although the mine's been going on for years. They may break the rules and say, okay, let's take that value of spilled energy and assign it to putting in some hydrogen technology. We see at Cooper Pedy that they are spilling a lot more energy than they originally anticipated. And so there's an opportunity to do the same. The life of that mine, because there's a town attached to it, is far longer. But any new greenfield mine that was, you know, in that 10 to 100 megawatt and greater in size today would seriously be considering the integration of hydrogen as part of their production, especially if it's remote, because there is so much uncertainty around where gas prices are going to go, where diesel is, even the security of the fuel at the moment. We've seen what's happening in the Gulf of Oman, the trade wars that are currently happening. We have 21 days of diesel reserves in country. If that gets disrupted, our economy could come to a standstill within months. And we need to take these things into account. We could be on a burning platform as far as this is concerned. We need to look at the alternatives.
Fully agree with what Warner just said. Obviously, the Pilbara imports several billion litres of diesel a year. Obviously, with escalating trade tensions, the South China Sea, sort of maritime access issues, the Gulf of Oman, it's not inconceivable to foresee a situation where diesel supplies were threatened. So what is the opportunity cost of that to Australia, to the mining sector, of having supplies of its primary source of energy cut off? So there are other reasons than just cost. It's also about energy security and avoiding an opportunity cost of disruption.
So just a quick question for my fellow panellists, I suppose. I'm curious about the fuel stuff, the electrolyzer side. I know, speaking of gas turbines, say that you did have a scenario where the mine life was relatively short. We would certainly advocate at the end of that mine life, you pick up the gas turbine. It's a modular unit, skid-based, you move it to your next location. Is the same principle apply to an electrolyzer? I mean, say even after 15, 20 years, that electrolyzer can be redeployed? I mean, is it likely to hold any residual value?
Yes. These things can be moved around, just like a gas turbine. So, and that can be designed to be more mobile. But I think where life of mine is a concern, this is where his project makes sense, because he could be potentially a supplier of hydrogen to multiple mines in the area, and the production of that hydrogen on the actual site might not be necessary.
Well, to add, I mean, we've deployed 1,500 electrolyzers. I think 98% were in containers, so easily deployed. Both our technologies can be recycled as well. The PEM stacks can be recycled. Lifetime depends on how you use it, but let's say 15 years, you can recycle the stack as well, so that the long-term life is still available for a very, very long time for electrolysis equipment, and very easily redeployed.
Great. So how is this market developing? Which suppliers and miners are taking the lead on testing and introducing hydrogen into remote power systems?
Well, we saw some presentations today, I think. Yeah, I mean, at least from our side, there's been interest. FMG, I think, did a great presentation today, and They seem very keen. They have a hydrogen department. BHP and the other miners are all here. So I think they're all feeling it out, what makes sense. But what I said earlier is, especially from the OEM perspective, they said they don't have the equipment. You know, when I listen to them, they say we don't have the diggers that are hydrogen-based, etc. You got to tell your suppliers, give me a digger that's hydrogen-powered or fuel cell-powered. Find me a solution from an integrator like a company we work with, Ant here in Australia, or Siemens, that can give you an integrated solution using hydrogen and fuel cells on our site. So I think the miners have to push back on their supplier network and tell them, this is what I want, you find me a solution. Give me a cost on maybe a trial, and then give me a cost on mass adoption. And I think that's what the miners, if you don't mind me saying, have to do today, is push that gauntlet to look at large-scale projects, because they have the capability, they have the big minds.
Yeah, I'll just add to that. We see real opportunity where a number of key ingredients exist, I suppose, for our technology in particular. So, for example, a project we are supporting with H2U, many people obviously know Tilio and his project in Port Lincoln. You have a situation where you are looking to develop a plant on the very fringes of the grid, if you like, prone to disruption in reliability of electricity. You know, with obviously deep personal experience in that part of the world around an outage that caused significant pain, looking to provide an insurance policy essentially against a similar outage, in a jurisdiction which I would say is relatively more supportive of supporting renewable type projects, including green ammonia projects, and sitting in a location where you have a large potential offtakes. For example, you're sitting in an agricultural region where the ammonia has a ready-made home, if you like. So once those three ingredients intersect in such a case, you know, we see real potential.
And for me, it's not just about embracing hydrogen; it's about embracing renewables broadly. So obviously, you know, renewables have a zero fuel price risk, zero carbon price risk. Effectively, you know what the forward energy price is going to be. And so that can extend mine lives, it can increase global competitiveness, and obviously increase sort of social license as well. Obviously, market pull for cleaner, greener products is growing. So I just think embrace the opportunity of renewables broadly, including hydrogen, but it's not just about hydrogen.
So when can we expect to see hydrogen storage being utilised on a large scale?
So we're expecting to see projects at a reasonably large scale. I mean, I talked about the one in Tonsley Park, where we're injecting the hydrogen into the gas network. That should be up and running in the first quarter of next year. Larger than that, I would say for mining operations post 2023, we could expect to see that double-digit electrolyzer come onto mining operations. Small towns, remote area power systems for towns, probably slightly sooner than that. But before 2025, definitely.
I mean, it could be earlier. We've signed a project in Canada for 20 megawatts. I think that's roughly 4 times larger than any other project. I'm sure most of the suppliers in our industry are in discussions on very, very large projects in the 40, 50, there's even discussions on hundreds of megawatts. So, and that's where it comes down to the goal of the electrolysis business is to get where we are on steam reforming. And because of low-cost renewables, we're getting close on very large systems, of course, but that'll take a bit of time to deploy those projects. But it really depends on the project developers. It could be a mining company, it could be a gas company. We're not sure today, but as we talked about earlier, the first mover advantage is for the companies that want to move into that. For us, on the fuel cells, it was the trains in Europe. Alstom was the first company that said, we want to do trains. We did the commercial trains. Now we'll be deploying to 4 different countries in the next year. So that area is growing very quickly, and we're seeing a very good economic structure for it. If we see the same in electrolysis on very large scale, I'm sure the economic structure will dramatically change, not just for us, but all the suppliers in our network as well.
Great. So addressing technological advancements and market developments, When could we see an acceleration in the uptake of hydrogen in remote mines?
Look, I'll say that we are already seeing, even since I can just speak from personal experience, this is probably my third hydrogen-related conference, I suppose, in the last 6 months. I see a lot of the sort of familiar faces around here, and from the day of my first exposure to I'm coming from a traditional oil and gas background, but from that first interaction with the hydrogen community, if I can call it that, to today, if I could just purely judge on anecdotal kind of inquiry and interest from the broader mining community, it's been huge. So, I've met with many people in this room specifically about their interest and intent to start leveraging this technology around capturing renewables, electrolyzers, and hopefully in our case then putting that through a gas turbine for power gen. In many cases you have miners who are running on existing technology very similar to that we're developing for hydrogen. So the questions then become, rather than buying a new turbine, what can we do to retrofit our existing kit to enable us to sort of make that switch in a kind of more stepwise kind of manner rather than a quantum shift in your infrastructure. So yeah, in summary, it is happening, and I see at the moment there's a lot of sort of inquiries, I'll say, and we haven't seen too many solid, obviously, orders yet and that sort of thing, but absolutely the interest is growing exponentially, so I would expect in the next few years, hopefully. I'll just add one sort of footnote to that, in that I did hear a comment earlier in the day from a gentleman who sort of raised the concern, which I kind of share, I suppose, around the fact that we did have a similar conversation around the switch from diesel to LNG some years ago, and I had personal experience around pursuing that avenue around supporting diesel displacement, virtual pipeline, etc., and here we are today, I suppose, now shifting to the next fuel, and of course we now support that fully, but we want to make sure we're doing everything we can to make sure this is really the fuel for a long-term future for us. So I'm interested to sort of work with people to understand how we can make that happen.
I think they'll reach a point where there'll be an inflection where suddenly it will accelerate really quickly, because if you're not embracing renewables, including hydrogen fully, then you're losing competitiveness against those who do. So I think we're still kind of trying to get over the hump, but I think they'll reach a point where it really accelerates quickly.
Yeah, and as far as the technology is concerned, our third generation electrolyzer, there's very little room for technological improvement. It is a mature technology. We've been delivering them as fuel cells into submarines since 1985, and it's the same technology, very little room for improvement. It's all about scale and market uptake. This will bring down the prices, and this is where companies like ARENA play a very important role, because they will help to make this technology commercial here in Australia, as they've done with solar. So, I can't stress the importance of an organisation like ARENA insofar as this technology is concerned, and the uptake and becoming mainstream.
We've done trials with Rio Tinto on small scale 5 kilowatt units for telemetry equipment. So we've done it already. We've done a large mine, or reasonable sized mine in Canada. So adoption is really up to the folks in the mining companies that are all out here. It's really up to you. The technology is there. It's up to you to find an application that makes sense on your mines. Figure out whether that's heavy duty transport, whether it's power, and decide that, okay, well, we're going to try this out, this hydrogen technology, because all the building blocks are there. It's a matter of you deciding on what you want to do and when you want to do it. So adoption could be tomorrow, it could be a bit longer if we move slower and wait on it. So it really depends on I think, the end customer, which is the large mining companies.
So to close out the loop, once our mine has closed, what options do we have to repurpose the hydrogen production?
So I'd like to paint a little picture here. So let's imagine a large 100 megawatt mine. It's used hydrogen as part of its hybrid power plant. 20 years later, it's end of mine. We've written down the cost of those assets. They've depreciated, but those assets are still able to produce hydrogen. So rather than taking your ore body from mine to port, you can now imagine that we're taking hydrogen from mine to port, and there is an opportunity to extend the life. You've got the renewables, you've got all the assets sitting there. You don't have the resource or mineral to mine anymore because it's end of life, but you're now producing hydrogen that you can now export out of port and send to port using those prime movers. So that's just an idea, but I'm sure that there are many other uses for that plant, mobilizing it and moving it somewhere else.
And if it's a short life mine, 5 years, as you mentioned, as I mentioned, they're all containerized. If that is an end of life, we can move that electrolyzer to a fueling station in the city. We can move the fuel cells to a remote community, native community in Australia. So these things are easily transportable, and one of the things we don't talk about a lot, and we should more, is the recyclability. Both the electrolyzers and the fuel cells are very easily recycled. Batteries, you can't say the same story. So that's another strength in our industry, is the ability to recycle these systems, both the PEM electrolyzers and the PEM fuel cells, that allows you to repurpose them and continue extremely long lifetimes for these systems and move them around.
Great, so we'll hand it over to the audience if anyone's got any questions.
Dominic Woodwell, I look after the gas portfolio for the Sino Iron project. We've got a 480 megawatt gas-fired power station up there. What does hydrogen bring, or the technology bring, to an existing brownfields operation? Is there a business case to bring it in and burn spinning reserve gas to generate hydrogen? Is there anything?
So on existing power plants, it really depends on a number of things. If you're operating your plant on natural gas and everything's going well, but you are concerned about uncertainty on gas prices or the availability of it, or you have drivers as far as your renewable share or your reduced carbon footprint, you could be looking at putting a large solar farm producing hydrogen and injecting that into your gas stream, increasing the calorific value of your gas and running your gas turbines as long as they can accommodate a 20 or 30 or 50% hydrogen content. So again, it depends on what your drivers are, what are your needs, what do you consider going forward when it comes to your sustainability drivers, and of course, again, a techno-economic assessment needs to be done to make sure that it makes sense.
Hi, Alistair Dick again from the Rocky Mountain Institute. I'd like to know a little bit more about, once the hydrogen is made, I've heard of it being stored at 700 bar in cylinders. I've also heard it being stored at 300 bar, 350 bar, and then the liquid hydrogen carriers. Has some thought been given to sort of, the whole safety discussion that we had earlier and the transportability of that, in the existing infrastructure? Are we finding sort of a common denominator of what the hydrogen carriers look like and what the technologies of the future look like for that?
Okay, so when it comes to storing hydrogen and the moving of hydrogen around, we've been doing it for decades. It's not a new thing. We're just talking about doing it at a much higher scale, so far more of it as we move to a hydrogen economy. And the pressures depend on the availability of the space and what you're going to use it for. So on a remote mine where you've got plenty of space, you would store it 100 or 200 bar. You spread it out. It's much cheaper to compress to 100 bar than 700 bar. That uses a lot of energy to compress it to 700 bar. But we need 700 bar if we're going to put it into cars. We need 350 bar if we're going to put it into buses or trucks. So it depends on where you're going to use it. Into a normal fuel cell for re-electrification on site, I think we're only 5 or 7, 15 bar at most. So you don't need much pressure. But if you want to store it, and I mentioned earlier in my presentation, a 40-foot cube container will hold 35 megawatt hours of energy at 500 bar. So if space is a constraint, you're going to increase the pressure. As far as the carriers are concerned, there are a number of possible carriers, LOHC, toluene, ammonia. I'm a fan of ammonia. I believe it is going to be the way we move considerable amounts of hydrogen around long distances, specifically for export. So companies like Yara and Orica could move into the energy space, and ammonia could be used not only to address our concerns around increasing our food production, but also energy security as our population grows to 10 million by 2050. So, you know, there are all sorts of ways of compressing and moving this stuff around.
And on the safety question, I'll bring out the elephant in the room. There was a fire in Norway at one station. So we were trying to figure out how we're going to talk about this. In the US alone, there were 6,000 petrol station fires, just 1 year. So when you talk about safety, people who work with hydrogen, at least our general belief is it's far, far safer than petrol or diesel. It's 14 times lighter than air, so it dissipates in the atmosphere. If it's confined in a very small area without any ventilation, sure, it's dangerous. Any gas is. But when you look at LPG, petrol and other gases, they all pool together when they leak. Far more dangerous than hydrogen. So I think if you get used to hydrogen and you know hydrogen as a gas, everybody in the industry, I think we all know it's far safer than other gases, but again, it's education and understanding, and we all have to get there, and it does take time.
I think if it was the other way around, and we were a hydrogen economy considering going to petrol vehicles or ICE vehicles, we'd never go there because of the dangers associated with it. We've just become really accustomed and complacent as far as petrol fuels, which pool. We know that there are deaths every week as a result of fires on vehicles, people getting burned to death. You see it in the newspapers every day, just in this country. So this hydrogen fuel station that blew up in Norway last week, no one was killed. In fact, the only injury, 2 people were injured. They were in their cars at the time, and they were injured by their the bags that blew up.
It made a sound and the bags popped out.
Airbags in the car, and they hurt 2 individuals in their car. So no one was hurt other than these airbags deployed.
Okay, so that concludes our panel. So thank you for joining me.
Thank you.
Thank you.